All right, so I just finished deriving, or at least justifying, the expression for calculating how much the length of a essentially one-dimensional object, we're going to just treat it as one-dimensional for now, how much its length changes as you change the temperature of the object. And the argument that I made, more hand-waving and reasonableness than any proof, but whatever, is that the length change depends on how big the temperature change is, what the material is made out of in the form of this constant here that's called alpha, the coefficient of linear expansion, and then perhaps not quite as obviously, how big the object was to start with. Okay, and so the coefficient of linear expansion, as I say, is a value is a constant for a given material, somewhat like the resistivity of a material, like the coefficient of friction of a pair of materials, things like that. Okay, so let me do a quick example here, or a couple of examples. Suppose I have a 10 centimeter long aluminum rod has its temperature change by just, look at my different screen here because I put it on a different screen, have its temperature change by just 10 Kelvin. How much does its length change as a consequence? Okay. Since I've already sort of got my diagram here, I was using it before, so you can think of this as our 10 centimeter aluminum rod. The length of the thing is going to increase. Now, technically, as I've mentioned before, its dimensions, all three dimensions are going to increase, but because its length is so much larger than either its height or its thickness, we'll, for now at least, ignore those other two dimensions and just think about the length. And so as the temperature increases, actually I didn't say that it increased, I just said its temperature changed, but that's all right. Let's imagine for the moment, let's be definite and say that it was an increase in temperature, in which case these particles, as I argued in the previous recording, are moving faster and faster and faster, which means that they travel more distance before they collide with some neighboring particle, and that represents then a slight increase. And I'm going to draw it on of its dimensions, and I'm going to draw it on both sides because it does expand in both directions. Okay, and that was a pretty subtle change in my drawing there. So there you go. You can see right there, this little green area here, and that little green area there. Okay, and that's the change in temperature. I'm sorry, the change in dimensions that I'm imagining. All right, and there's nothing terribly difficult about this mathematically, just pretty much plug and chug. So the change in temperature is going to be alpha, which you have to look up, and I did look it up, and it turns out for aluminum, it's 23 times 10 to the minus 6 per Kelvin, times the original length, which was 10 centimeters, or 1 meter, 0.1 meter, and then a 10 Kelvin change. Notice quickly that the units work out the way that you think that they should. We end up with units of meters here. And I worked out these numbers. Happily, 10 times 0.1 is just equal to 1. So this works out to be 23 times 10 to the 6th meters, or 2.3 times 10 to the minus 5th meters, which is 0.023, 3 millimeters. So roughly 2/100ths of a millimeter, which is not large. And this now admittedly, the thing was only 10 centimeters to start with, and a 10 Kelvin changes, and you'd notice it with your fingers, you know, if you felt it, that its temperature increased or decreased by 10 Kelvin, you could feel that change, definitely. But it's not going to be tremendous. It's going from 60 degrees to, it's going from, 20 degrees to 30 degrees. That's noticeable. It's not going to be dramatic, but it's noticeable. But the size of the thing doesn't change by all that much. And that corresponds to your normal human experience. You don't, as an ordinary matter, notice things growing and shrinking, increasing and decreasing in size on a day-to-day basis. These are very small changes as a general rule. And aluminum is one of the largest ones. Glass, for example, is just 9 times 10 to the minus 6, right? So roughly 20 times, in other words, it's somewhat less than half of what aluminum is. So glass changes distance correspondingly less than aluminum does. So pretty straightforward there. I'll even say that here. A thing worth noting here is, although it is true that different materials have different values for the coefficient of linear expansion, the different values of alpha, the differences tend to be not tremendous. For almost all materials, this exponent here is 10 to the minus 6. I mean, the exponent is minus 6. So it's very unusual for a solid to have a coefficient of linear expansion much different from this. And that's a very short recording, but conceptually, this is where I wanted to stop. So in our next recording, the next lecture, we'll extend now to 2 dimensions.